Hello, good morning. This is Mr. Williams, and I'm recording this video at around 9:15 in the morning on March, yeah, not May, March 3rd, 20th, excuse me, 2020. This is already our fifth digital learning day. You've made it through an entire week so far. And just as a quick reminder, we have next week is again officially a digital learning week as well for Gwinnett County Schools. And the week after that, the week starting on March 31st, that's still going to be our scheduled spring break. So I don't know how your plans have been affected for spring break, but regardless, we will, not be in school that week, of course, and there will not be any digital instruction. You can perhaps do put in some time working on missing assignments or something, but there will be no new assignments during the week of spring break. And again, that's not next week. Next week does have instruction. Spring break is the week after, the week starting on March. I think it's actually March 30th, but anyway, the week that includes the 1st of April. And I'm going to go ahead and turn on my presentation mode, because I actually already started recording this video a few minutes ago and didn't turn on the presentation mode, so I kind of wasted a little bit of time. But this time, that's not going to happen. So like it says, I'm presenting to everyone. That's good. I want to go ahead and show again our e-class page, just a couple of quick reminders. Going to the actual home page, again, today's announcement post is pretty bare bones. It just reminds you, okay, click here to get started. So if you click on the link, it'll take you to the proper instructions. And again, it talks about, like we said, next week on spring break. It also reminds you, and this is one thing I emailed and posted about on Wednesday, and I also posted again about it yesterday on Thursday. You should have already started watching the free online PBS Nova documentary, Black Hole Apocalypse. If you've not started watching that yet, you need to at least watch the first 50 minutes today. And that's why I asked y'all to start watching it as early as Wednesday, because I didn't want you to have to necessarily spend that much time watching it just today. These assignments don't have to be, incredibly long, but if you haven't started watching the video yet, it might be a little bit long for you today. So what I did decide as I was working on the assignment yesterday evening is for the questions today for the video only cover about the first half of the video, because it is a longer video. And that's why it says you need to have watched at least the first 50 minutes. That's actually just the first half. So today's questions, if you watch at least the first 50, not 15, 15, minutes of the video, then you will be set for answering the questions from part one. We'll look at part two on Monday. And again, the PowerPoint we're going to be talking through, the link to the PowerPoint itself is right here. And another thing you can do just for fun, or actually also as a grade replacement opportunity, is this video from Mr. DeMaio. He's a YouTube personality, and he's also an elementary school teacher up in New Jersey. And he's got a very quirky, weird video on black holes, but it's a lot of fun, and might just be worth watching if you just want to watch it. But there are also, I do have questions for it as well. And you can just answer them for fun if you want, or if you have a missing assignment from this unit 3, you can replace it by working on this assignment here. And I'm going to leave that open really throughout almost all of next week. So it doesn't necessarily have to be done today. It can be done over the weekend if you want, or during next week as we work up until our Unit 3 test. And again, like it says here, if you would like some more supplemental videos, go to my YouTube page. I've decided just to, instead of reposting every video on eClass, which is a little time consuming, I've just got my playlists up here on YouTube. So this one right here says Stellar Life Cycles and End Stages. That's the one that I've got pulled up right now. It's got my neutron star lesson from the Wednesday, I guess. Yeah, Wednesday. And again, also a bunch of black hole themed videos. And I also have the relativity playlist from yesterday, which includes both of my lessons from yesterday and also a bunch of other ones. So, again, if you got free time, check out some stuff, at least one or two things. It'll help kind of just, reinforce what we're talking about here in class and what you're working on in the lessons or on the assignments. Okay, so with all that said, let's go ahead and get into the actual lesson. And that is going to be broken down into two parts like we did yesterday. So I'm going to go ahead and go to present mode, turn on my laser pointer. Again, we're still in AKS 8C2. This is, again, the material we've been looking at for the past couple of days really still falls under this particular AKS. But anyway, like it says, we are back to black holes after taking a detour of sorts with relativity yesterday. And we're going to start by looking at how black holes are formed. We've kind of been over this with our lesson on high mass stars. But like it says, so far, we have implied that black holes can only form from the core of a former supergiant or maybe hypergiant star, and the core has to be of at least 3 solar masses. And that's, generally speaking, that's true. That's true for most realistic scenarios in nature. But theoretically, we could actually turn anything into a black hole. This is because the key to a black hole is not about the fact that it comes from a star, but about the fact that the mass that you're dealing with, the mass in question, has to be reduced to take up 0 volume. If you do this with any mass, you will be making a black hole. And so the mass doesn't just have to be a star core, it could be a planet. We could actually theoretically, again, not necessarily practically, but theoretically we could turn, say Jupiter or Earth into a black hole. I could turn a refrigerator into a black hole. I could turn myself into a black hole. That's a career goal at some point, I guess. But again, as with a massive stellar core, any object we might want to turn into a black hole must be compressed. Again, just like how gravity works against a massive stellar core to compress it to take up 0 space and have infinite density, we would also have to be able to do that to whatever random object we are attempting to turn into a black hole. So what's interesting, though, is we can, even though we can't practically do this, you're not going to be able to find some random object at home and just, squeeze it until you turn into a black hole. You don't have the kind of force available to you that gravity does when it's acting on a supermassive, stellar core. But we can actually calculate how tiny we would have to make an object in order for it to become a black hole. And that leads us to this next slide here. And when we calculate this, we're finding something called the Schwarzschild Radius. And that is how you say that. It's not Schwarzschild. You do hear some people saying that, even some pretty smart people, smarter people than me, but apparently, and this is something I've known for a little while now, apparently the correct pronunciation is Schwarzschild, or at least that's as close as my English accent allows, because it's a German name. But the Schwarzschild radius is the much smaller size that an object must be compressed to so that it can become a black hole. And this is the formula right here. Rs equals 2gm divided by c squared. And what do all those figures and factors mean? Well, R subscript S is the radius in question, the Schwarzschild radius, and it's measured in meters typically, unless you change some of the other measurements for some of the other factors. And big G, if you remember, again, we deal more with this in physics than we have in our astronomy class. But if you remember back last fall when we talked about Kepler's laws of motion, we also talked about Newton's universal law of gravitation. And in his formula for calculating gravitational force, there was a constant, and it's listed as big G, capital G, and the actual measurement, the number is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And so you do have to include that figure in this equation as well if you're going to calculate with it. Capital M is going to be the mass of the object you're trying to compress. And again, this is typically measured in kilograms, or it has to be measured in kilograms, unless you're, again, changing some other things. And then C, of course, like we discussed yesterday in the relativity lessons, is the speed of light. Again, if you round that up, that's roughly 300 million meters per second. And what's interesting here is, and I didn't include the other formula, but if you write out the formula for calculating the escape velocity from an object, like for example, if we want to put a satellite in space or a space probe in space, we have to have a rocket that can go fast enough that it can leave Earth's gravitational well. And that's called escape velocity, that particular speed or velocity. And so if you take the formula for escape velocity and you rearrange it to solve for the radius of the planet or object you're trying to leave, because that's one of the factors in the escape velocity formula. And so if you rearrange to solve for that radius, and then if you substitute the escape velocity with the speed of light, you get the Schwarzschild radius equation. So what you're really solving for is you're saying, okay, how big does the planet or star or whatever I'm near need, how big does it need to be, or really how small does it need to be in order for me to have to go the speed of light in order to try and escape it. And that's a little bit of a misleading way to put it because, as we'll see, even at light speed, you can't escape a black hole. But mathematically, that's how this equation is derived. That's just kind of a neat thing to me. You take something that's a little more practical, like escape velocity. Again, people who put things into space, satellite companies, SpaceX, etc., they depend on that sort of thing all the time, and then turn it into something much more, weird or exotic. So the Schwarzschild radius right here at the bottom, the Schwarzschild radius also defines what we are going to call the event horizon of the black hole. So a little more on Schwarzschild radius here. If we were to take the sun and calculate its Schwarzschild radius, so, include its mass, include c, or the speed of light, as the velocity that's involved here, we would actually find that we would need to compress the sun down so that its radius, not the diameter, but the radius, could only be 1.8 miles, not even 2 miles. Again, you can walk that in fairly little time, or run it even quicker. So again, taking something that's as big as the sun is, again, roughly 100 times larger than the Earth, and making it only not quite 2 miles. That's what it would take to turn the entire sun, all of its mass, into a black hole. Now, scaling down the Earth, if we take the entire Earth and try to turn its mass into a black hole, we would have to squeeze it into 0.009 meters, which is to say 9 millimeters. That's how small we would have to make the Earth in order to make it into a black hole. Obviously, either of these things are not going to be very easy to do, but again, it's just kind of fun to talk about these from a theoretical standpoint. And just to point one thing out, the diagram here, the figures it uses does conflict a little bit with the figures I have here. The figures in the text are a little more accurate, but I think the diagram still gets the idea across. Again, taking things that are tremendously large, at least compared to us, and then making them much more manageably sized. So moving on. All right, so basic structure of a black hole. And these are terms you're probably familiar with. If you have ever learned anything about black holes before, whether just of your own research or through movies or whatever. Science mug, shout out here. But there's two main structures, two main parts to a black hole that all black holes have, at least in some form. And the key one, of course, is the singularity. And the singularity is, I guess, the black hole proper. It's where all of, we talk about black holes being formed because their mass, the mass of a stellar core, has been compressed so it takes up zero volume, zero space, and therefore it has infinite density. The singularity is what we're talking about when we say that. So this is where what we know about the laws of physics breaks down. Again, you can't, when we say, okay, we'll compress something of at least 3 solar masses into zero space, that doesn't make any sense. Again, you just think about it yourself. Even like a really simple example, like, maybe you've had this challenge posited to you before, where someone says, hey, take a sheet of notebook paper and try to fold it 11 times. You can't really do it. The tensile properties of the paper don't really allow them to be folded, and the paper kind of gets stronger per se as you get increasingly more folds. And similarly, if you try to take any mass and try to compress it to as small of a point as possible, you just wouldn't be able to do it under your own power. But in fact, gravity does do this, and we have observational evidence for this in certain black holes we've detected in other parts of the galaxy, or outside of the galaxy, and so on. And of course, the singularity is also interesting because it seemingly violates some of the stuff we know about basic ideas or laws of physics, like conservation laws, conservation of energy, conservation of mass, conservation of information. All of those things, to our knowledge, or as far as we know, are lost when they enter a singularity. There's no getting them back. They're destroyed, as it were. And because that so goes against some of the basic laws of physics, there are some astrophysicists who really, they have some other things that they can tell us about black holes, some alternative theories about what goes on with a black hole. And we'll touch on a little bit of that later in the lesson. Now, surrounding the singularity, and this is something I didn't really get into in the text, of the PowerPoint, but a singularity is never found, at least, again, based on what we know so far, both observationally and theoretically. A singularity is never found by itself. We don't have any naked singularities out there in space. They're always surrounded by this event horizon boundary. And again, the event horizon is as far from the singularity as the Schwarzschild radius that you would calculate for, again, whatever stellar core that may have formed the star or formed the black hole. And so it's going to be that particular distance. And again, the event horizon, it's called the event horizon because basically beyond it, you're not going to see anything happen. We'll kind of get more into this on the next slide. But it says it's also, you can also refer to it as a point of no return for the black hole. So it's possible to survive passing an event horizon, at least again, theoretically, and for certain black holes. For some black holes, you actually wouldn't survive. We'll talk more about that. But if you did pass through and survive crossing an event horizon, again, you might live and continue to experience things for some time after that, before entering the singularity. But you would have no way of turning back around if you changed your mind and said, I don't know, I don't really want to enter the black hole and go in the singularity. I'd like to go back to my spaceship. Once you've crossed the event horizon, that's no longer a possibility. Like it says here, your only possible destiny once you've crossed the event horizon is the singularity. It becomes the only place you can eventually go, and it's the only possible future you have. It's kind of an interesting thing. And there's one video, and I actually forgot to put it on my playlist so far. I'll do that sometime after I record this. But there's a video where I watched it a few weeks ago, and this guy does a really good job discussing black holes as temporal or time-based singularities too. Just like how you can't avoid, today's Friday, you can't avoid next Monday coming back around. Eventually you're going to run into next Monday in the sense of time passing. Once you've crossed an event horizon, the singularity is an unavoidable future for you. A little more here on light. Again, black holes, they're called black holes because presumably we can't see them. And that's true if the black hole is kind of just by itself. We'll talk about some situations where, well, the black hole is a little more easily able to be seen because it's got a bunch of things going on around it. But the reason why we can't see them is any light that enters the black hole, or even just the event horizon, again, also is not going to leave. Just like how if you were to enter the event horizon, it's a point of no return for you. It also is a point of no return for any light that enters it. And that's what's being shown by this particular light ray right here that spirals in through the event horizon. All these other light rays either circle the black hole or get deflected by it, but they don't get trapped inside the black hole, unlike that one that kind of decays into it here. All right. So again, approaching a black hole. This is, again, things I do not recommend. Big old DNR, do not recommend. But hey, theoretically, it's fun to talk about. So as discussed in the relativity lessons yesterday, to an observer in normal spacetime, meaning not really strongly curved by mass and gravity, someone approaching the event horizon will seem to slow down. So again, if like this robot probe in the diagram, if I'm the observer over here with my giant book bag, if I watch the robot probe approach the event horizon, time would seem to slow down for them from my perspective as the observer. They would seem to be moving incredibly slowly. And the black hole apocalypse video, again, it does a really good job of trying to discuss and visualize this. So definitely, again, you should have already watched the beginning of it anyway, but definitely make sure you look at that today. And the image of the person, because if I can see something, that means I'm seeing light reflected off that object or produced by that object. The image of the person transmitted by light, kind of like this light ray right here, would also be increasingly more red and then invisible at a certain distance if the observer is moving farther away. So like for example, right now, me as the observer, I'm standing at a 10,000 kilometer distance. And at that distance, any visible light from the person nearest the black hole and near the event horizon will become like, I won't even be able to see them because the light that's reflecting off of them gets redshifted so far that it actually becomes radio waves. And of course, you can't see radio waves. Now, I could pick up a signal, with an antenna or something, or a radio telescope perhaps, but I would not be able to literally see them with my own eyes. If I kept getting closer and closer, I would still see them. But again, that would have to be getting kind of dangerously close to the black hole myself. This this shift towards the red end of the visible spectrum or the radio end of the entire EM spectrum is called gravitational redshift. This is not due to the Doppler effect, like you can have by an object producing light waves moving closer or farther from you. Instead, the shift here towards less energetic forms of EM radiation is caused just by the energy being expended by the waves trying to basically crawl out of the black hole's gravity well. They're not escaping from the event horizon. Keep that clear. These are light waves, or in this case, this one right here, you can see with my laser pointers and X-ray. These are waves that are simply near the event horizon. They have not crossed into it. And another thing, just to point out, I said it takes a lot of energy for these light waves and other waves to escape from near the event horizon. And again, part of that is because even though they're going from our perspective kind of a short distance to get away from that sort of near zone there, from their perspective, they're actually going a very long way because of how curved space-time is going to be. It's going to be almost kind of squished. So from our perspective, they're not going that far, but from their perspective, they're actually going a very, very, very far distance. Kind of like how if the LIGO detectors from yesterday's lesson, if they detect a gravitational wave, that means the laser in one of the two LIGO detector arms has actually traveled a farther distance than the laser in the other arm. Similar process. Okay, so actually entering the black hole. Again, other things to not recommend, but fun to talk about. So as an object or person approaches the black hole, and the exact distance at which these things start to happen will really depend on the mass of the black hole. Again, that's coming up in the lesson. We'll get to that. But, excuse me, the exact distance will depend on the mass of the black hole. Once a person gets close enough, the difference in the gravitational force on the side of the object nearest the black hole and on the side of the object facing away from the black hole, that difference in gravitational force will be very, very big. It'll be at least 100 times, maybe even more. And so, like, for example, and again, Jan 11, shows this sort of example in the black hole apocalypse video. If you try to fall feet first toward a black hole, then the forces acting on your feet will be much stronger than those acting on your head, kind of like we see in this diagram here. And eventually that leads to what we call spaghettification. And again, that is a real astrophysics term, but it's called that because the gravity pulling on your feet would be so much stronger than that pulling on the top of your head that you would be stretched really, 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 really long and thin along the axis leading to the singularity. And by the way, just another quick reminder: this is a term we've seen in the fall semester, but this difference in gravity on one side of the object versus the other, we call that a tidal force. It's the same thing that produces tides on the moon, just obviously in a very different sort of scenario. Now, again, I mentioned that the fact that things entering a singularity would kind of violate some of our basic laws of physics. Because of that, some people suppose and theorize. And when I say people, I don't just mean like, a random person off the street. We're talking about very intelligent astrophysicists. They suppose that entering a black hole would actually cause the immediate destruction of an object. And when I say that, I mean like entering the event horizon. And they call this a firewall. And this is thought to exist possibly because there might be something going on at the event horizon of a black hole called Hawking radiation. And if you've already watched the Kurzgesagt, again, I don't think I'm saying that correctly, but if you watch their video on black holes, their main one that we've had on E-Class for a couple of weeks, they talk about this. They talk about how Hawking radiation at the edge of a black hole, at the event horizon, could actually cause the black hole to lose energy and therefore mass over time and eventually actually just evaporate. And but all of those particles, all these virtual particles leaving the event horizon could have a lot of energy, and therefore approaching the event horizon might actually be quite dangerous. It might be too energetic to survive, kind of like, trying to put your hand on the stove, just too hot. And it would potentially destroy anything trying to enter the black hole. But again, that's that you see that explanation a lot less often than you see the whole spaghettification idea, where things just enter the singularity. Now they might be destroyed before they enter the singularity, but they are allowed to enter the singularity in that model. Okay. Oh, and look, hey, there's me getting spaghettified as I enter a black hole. I don't remember when this happened. maybe it just wiped my memories of the event. I don't know. Now, again, talking about going near a black hole and so forth, what's kind of interesting is that the mass of a black hole will actually dictate how safe it is to be around. Like how close can you get to the black hole without starting to suffer some ill effects, whether it's, again, running into a firewall or, again, being spaghettified and destroyed before you enter event horizons or after you enter the event horizon. So like it says, the larger a black hole is, the farther its event horizon is from its singularity, the safer it would be to approach. And since the event horizon's distance is set by the Schwarzschild radius, and that radius is determined, at least in part, by the mass of the black hole, this means that the most massive black holes are, in fact, the safest to approach. If you've seen Interstellar, they actually talk about this. They kind of really quick run by the explanation for it, but the black hole in that movie, Gargantua, is a supermassive, really big. And supermassive is the technical term, but it's a supermassive black hole, and therefore it's safe potentially to cross its event horizon. This is not really true for smaller black holes. So if you have a more typical size black hole, kind of more of the type we've been talking about, what we will call stellar black holes, they would be very dangerous to approach. Even before you would be able to get to the event horizon, at least within a certain range, you would be torn apart by those tidal forces of gravity that we talked about. And another thing that's also a little bit of a misconception that some people have with black holes, a lot of people assume that if there was a black hole nearby, it would just kind of suck up everything around it. When in fact, they're not any more gravitationally dangerous on large scales than any other star or planet would be. For example, right now, we live on Earth, and Earth is, around 93-ish million miles from the sun. We're in no danger of being immediately drawn right toward the surface of the sun and fried up. And that's because the sun has very powerful gravity, but the most extreme effects of that gravity are only really noticed once you get really close to it. The only planet that's experiencing anything like what we're talking about is Mercury, where it has its orbit distorted when it comes close to the sun with its perihelion. And the same thing would be true with a black hole. If you replace the sun with a black hole, we'd have some other problems like no, warmth and light and so forth from it. But gravitationally speaking, we wouldn't find any difference if the black hole had the same mass as the sun. And so we'd still have to, again, if we replace the sun with a black hole, we'd still have to travel really, really, really close to it in order to have any danger of being sucked into the black hole. Okay. And this next part is going to look at how we can classify black holes. And actually, that's where I'm going to end this part 1 video, and that's where part 2 will pick up. So I'm going to go ahead and take just a second here as I exit the presentation mode, and then I'll stop recording. Okay. So we'll go right back here. We'll just stop presenting and stop recording. See you in part 2.